My name is Julia Anton. I have a PhD in neuroscience, and today I'm going to talk about the HPN technology and how it's affecting the brain. To do that, I'm going to do a little bit of basic neuroscience and a little bit of basic electrical engineering, and finally talk about the technology and how it's stimulating the brain. And I will talk a little bit about some related technologies and how they work in the clinic. So the neuron is composed of a cell body, like other cells in the body. What's unique to neurons is it has appendages called dendrites, and those come out of the cell body area. And then it has one axon that leaves the cell body, and that goes to other neurons, and that's how it communicates with them. At the end of this axon, there are synaptic terminals, and that's where neurotransmitter is released, and it communicates with the postsynaptic cells. And postsynaptic cells sense these neurotransmitters through receptors, and then it responds to that and might send a signal onto the next cell. So these neurons use the axon to communicate to the next cell through electrical current. And when the current comes to the end of the axon, neurotransmitter is released, and that's how the cell communicates to the next cell. And neurons accomplish this by maintaining a negative ion potential inside their cell. So the inside of a neuron is negative relative to the extracellular space. And it does this by separating charged ions. The ones that we care most about, that I'm going to talk about, are potassium and sodium. So potassium is very concentrated inside the cell and not as concentrated outside the cell, and sodium is the opposite. There's a lot more sodium outside the cell than inside the cell. And then crucially, inside the cell, there's a lot of charged proteins, which makes the cell more negative than the outside. So along the cell membrane, there are ion channels. The ones I'm going to talk about are for sodium and potassium. And the sodium channel is generally closed because there's a big ionic gradient that will cause sodium to rush in if they're open. Potassium is a little bit different, and that's because there's two forces on potassium. One is a diffusion force that goes outside of the neuron, so it wants to go out because there's not as much potassium outside the cell. But there's an electrical force keeping it inside, and that's because the cell is negative and the positive potassium is attracted to the negative cell. Synapses are propagated down the axon by triggering sodium channels to open and causing the depolarization. And as one part of the axon is depolarized, the part right next to it becomes depolarized as well, and it's sort of a chain reaction. Following that, the potassium channels rectify that depolarization by opening and causing the membrane potential to become, again, negative inside. And you can just imagine this as a moving front going down the axon, causing electrical potential changes along the membrane. And so when it gets to the end, the beginning of the axon is at normal resting potential again. And you can imagine you have all these ions going back and forth, which are creating this depolarized state that neurons like. How do they get back in? So how that happens is there is a sodium and potassium pump that puts the ions back where they should be. So sodium on the outside and potassium on the inside. So the bottom line about all of this that I want to communicate is that so neurons are highly interconnected. They're always talking to each other, and this happens through electrical currents. So along each axon and at each synapse, there's a delicate balance of electrical charge and current. And so when you disrupt this balance, this is going to result in altered neuronal communication. And so this is important when we're thinking about HPN and injecting current into the brain. All of this very specific ionic current moving around is likely to be changed. I want to talk a little bit about electrical circuits, just the very basics so that we have some common terminology. In an electrical circuit, in the most basic sense, you apply voltage to a circuit, and that causes current to flow through a resistor and back to the voltage source. The typical equation is I equals V over R. I is the current, V is the voltage, and R is the resistance. So you can imagine that V over R means that if R, the resistance, is higher, no matter how much voltage you have, the higher the resistance, the lower the current flowing. And in our case, R is the skin electrode contact. So it's very important that there's a very close contact between the skin and the electrodes such that there's very low resistance and the current that you think you're putting in is actually what's going in. Current flows in different patterns over time. The two most important that I'm going to talk about today are direct current and alternating current. Direct is just what it sounds like. It's a constant current throughout time. And alternating means that it's going between positive and negative in a sinusoidal pattern. The one that HPN uses is alternating current. But there's a lot of research done on direct current stimulation, which I'm going to talk about in the next slide. So the most simple form of direct current stimulation are two electrodes on the head connected with wires to a voltage source. And very basically, it applies positive voltage to one side and a negative to the other, and current flows through the brain in one direction. And this generally happens between 1 and 2 milliamps. This is applied for 10 to 20 minutes continuously, and that's different from HPN. Transcranial direct current stimulation, or TDCS, it appears to be safe. It's been used in research and clinically. It seems to be effective for depression, chronic pain, alcohol craving, and stroke. A related technology is called transcranial magnetic stimulation, or TMS, and that also induces current in the brain, but in a slightly different way. It consists of a magnetic coil held over the head, and a magnetic field is induced by passing current through this magnetic coil. And you can look at the field lines that are in sort of magenta in this slide and see how the magnetic field is going into the brain. The advantage of magnetic fields is that they pass through the skull and the skin easier than direct current. And once that magnetic field enters the brain, it induces an electric current in brain tissue. TMS has been studied a lot in research and clinically, and it has shown efficacy in depression, hallucinations, drug craving, and PTSD. And it also has a very low incidence of unwanted side effects. It is also pretty powerful, and I'm going to get to the numbers in a later slide, but it is a powerful stimulation of brain tissue. So one of the questions that comes up in research is whether the current gets into the brain is actually induced and where in the brain it's distributed to. So this is a simulation of TMS and TDCS stimulation. And when I talk about TDCS, you can think of it as alternating current as well, or what's happening in HPN, because the distribution of the current should be similar, it's just that the polarity changes very quickly. But the principles of where it gets distributed in the brain should be about the same. So here you can see that TMS stimulation happens right under the magnetic coil where you would expect it to be, and TDCS has the most effect right under the electrodes. The important difference between TMS and TDCS in the distribution of the current in the brain is when we look at a finer grained mesh of the whole brain. So to the right, you can see two mesh outlines of a brain. The top is TMS, and it is, again, as you would expect. The maximum current happens right under the coil. And the disadvantage of TMS is that it doesn't go very deep into the brain. It's 2 centimeters at most, but it's mostly right on the surface of the cortex. Below that is a model for TDCS, and it does have hot spots near the electrodes, but the current actually goes throughout the brain in ways that are a little bit hard to predict without an individual's MRI. And I'll show some more examples of this in later slides. But the important part about this is that it's a more widespread stimulation with TDCS than with TMS. And so speaking about penetration into the brain, I want to just talk about the different layers of brain and skin that both of these technologies have to go through in order to get to the brain. So the first barrier is skin, and TMS does stimulate current in the skin because there are charged particles in the skin. The skull is very non-conductive, so nothing happens in the skull. It goes right through that. And the CSF is highly conductive, and magnetic fields stimulate a large electric current there, and then the brain is considerably less. So the border between the CSF and the cortex is where the most stimulation with TMS occurs. In contrast, TDCS has the biggest barrier with the skin. So when you put an electrode on the skin and apply a current, most of that current gets shunted through the skin. And then the skull is very non-conductive, and very little of it goes through, but some does. And so it gets to the next barrier, which is CSF, which is more conductive, and some of it ends up there. And then a very small amount makes it to the brain, but some does make it to the brain, and does affect neuronal activity. I'm going to talk about some numbers related to HPN and the related technologies, comparing the strength of the signal and the strength of the stimulation for each of them. I'm going to add in here ECT, or electroconvulsive therapy. This is a stimulation that's similar to TDCS and TACS in that it's applying a current across the head. The only difference is that the strength is much, much stronger, and it's used pretty exclusively for intractable depression. But as you'll see, if you can improve with a lower power therapy like HPN, it would probably be beneficial. So ECT causes an induced current density, or amps per meter squared, of 225. In contrast, TMS, which I mentioned is much stronger than HPN, is 3 amps per meter squared. TDCS, which is still stronger than HPN, is an order of magnitude smaller, 0.3 to 0.8, and HPN is 0.0056 amps per meter squared. In terms of applied amps or milliamps, ECT is 800 milliamps. TDCS is 1 milliamp, and for comparison, a AA battery is 0.3 milliamps, and HPN is only 0.02 milliamps. In addition, because HPN is only on for brief bursts, it amounts to only about 0.03 seconds per session, and I'll explain why that is in slides following this. But in contrast, TDCS is on continuously for, as I said, about 10 to 20 minutes. So there's a huge difference in amount of current that's being applied. Another way to look at it is the electric field that's induced in the brain, and that's in volts per meter. So TACS, this is a related technology to HPN, very closely related technology, induces an electric field of 0.4. In contrast, TMS induces an electric current of over 100, and that is a level that is capable of triggering action potentials. So this is going back to the earlier slides where I was talking about neurons talking to each other through action potentials being propagated down the axon. So TMS is actually capable of triggering these action potentials, whereas TACS and even TDCS are not capable of doing that as far as researchers can tell. What they do is they influence the excitability or the probability of firing, and they do change neuronal patterns, but not directly by triggering action potentials. And finally, peak power of HPN produces about 2 microwatts, and a AA battery is about 450 microwatts, so much, much less than your common AA battery. So the HPN stimulation consists of a very specific waveform and pattern. It's basically consists of bursts of a complex mix of megahertz frequencies, and this is just an icon for it, but basically it's an alternating current that's very, very fast, much faster than brain speed frequencies, and it's meant to just be a burst, just a very quick stimulus, and it's only on for a microsecond. the way that it stimulates the brain at brain speed is that it does a certain number of these per second. So imagine we're looking at 1 second of time from 0 to 1, and you have a series of bursts, 1 through 11 bursts. And what that constitutes for the brain is an 11 hertz stimulation, which is right in there at brain speed. 10 hertz is about an average speed of brain oscillations. And this causes the brain to feel an 11 hertz stimulation. So the HPN protocol, and there's a couple that you can choose from, but this is the basic protocol for what it's doing when you press the start button. It first detects EEG power, and it'll do that for 1 second, and it'll see for that first second what the peak frequency is. So here, this is a 10 hertz peak. And then it will determine the feedback frequency, and that's based on what you set to be the offset or what protocol you choose. So let's say it starts at 1 hertz offset. That means 10 plus 1 is an 11 hertz stimulation, like I showed in the last slide. In the next second, from 1 to 2 seconds, it does another power transform and finds the peak frequency there. Here it's still 10 hertz, so then you go to the offset frequency, which has now gone up 1 to 2 hertz. So you have 10 plus 2 equals 12 hertz. So for that second, it's going to stimulate at 12 seconds, at 12 times per second. And then again, in the next second, it's going to do another Fourier transform and find the dominant frequency. Here, it's a different frequency. This is now about 7 hertz, but my offset is 3. So 7 plus 3 is 10 hertz. So you can see every second is a different hertz feedback, and it's based on what the current power is in the brain and the offset. And this continuously changing feedback is desired. That's the point. It's not trying to entrain the brain, it's actually trying to disentrain the brain. So whatever it's doing, so say 10 hertz, the idea with HPN is to disrupt that 10 hertz, and it does that by applying that frequency plus an offset. And the offset is constantly changing so that it doesn't get used to just seeing an offset of the dominant frequency. So the idea is really just to send back a bunch of different signals at different speeds. So as I mentioned before, most of the current that's applied through electrodes to the skin is shunted through the skin, and that's because the skin is highly conductive, and the current density, therefore, in the skin is about 1.7 compared to 0.38 in the CSF and 0.1 in the brain. But as I pointed out before, current does get into the brain, even though much of it is shunted through the skin. I want to show a few more images about the current distribution in the brain because it helps for clinicians to understand what's going on when they're applying current using HPN. So at the bottom of this slide, you can see that there are patches of red, and some of those patches are right underneath the electrode, but you can see that there's places that are far from the electrode location that are also very red. And that seems to be the common finding with, this is an example of TDCS, but you can imagine the same distribution would happen with TACS. Current gets stuck in the little folds in the brain, and it can accumulate in places that are hard to predict. And so when you're applying current across the brain, it's hard to know exactly where it's going to end up. And that's part of the reason why with HPN we move the electrodes around so we can hit large parts of the brain as well as different little pockets of the brain. And this is another study showing another simulation of current distribution in the brain from TDCS. You can see the electrodes in red and blue on the outside of the skull. And so there's three different conformations here, and it might look a little bit uniform to you at first, but if you kind of look for the hot red spots, you can see they're distributed in what looks like random locations across the brain. And that's basically what I want to get across in this slide, is that it's not only affecting large swaths of the brain between the two electrodes, but it's also affecting pockets that are hard to predict, especially without simulations on a real MRI. So to summarize, neurons, like I said at the beginning, rely on voltage-sensitive ion channels to propagate their action potentials, and that's how they talk to each other. And when you induce a current in the brain, that current can influence how these ion channels are acting and how they're communicating between neurons. And this logically would modulate neuronal activity. TMS and TDCS have been studied fairly extensively, and they do show efficacy for a number of disorders. TACS or HPN follows similar principles, but is much lower power. The key to HPN appears to be the stimulation pattern and waveform that is responsible for its clinical success. And it's probably just a benefit that it's actually lower power than TDCS that should be a safer application. And finally, current distribution in the brain is widespread and hard to predict with TDCS and with TACS. The bottom line is that there's a widespread distribution across the brain with small pockets of current densities that are stronger and hard to predict without a specific MRI model. So what's important for a clinician to remember is that we want to hit as much of the brain as possible, and we want to change these pockets of current densities by moving the electrodes around. The size of the current that's applied in HPN is incredibly small, and it seems like a stimulation that's a microsecond isn't going to affect the brain very much. And there's a lot we don't know about HPN and how it's affecting the brain, but we do know that the brain is adaptable, that it gets used to things very easily and very quickly. So the idea that you would switch up the frequency of the stimulation makes sense, and it makes sense from the point of view that the brain is constantly trying to adapt to it, but it never can. So in that sense, it's disrupting the activity in the exact way that we're trying to disrupt activity. That the stimulation itself is so small, even though it's patterned at brain speed, the stimulation being so brief, I think it blows our human minds that would matter. But even if it's brief, all of those ions that I was talking about do feel that shift, even if brief, and that's disrupting the activity that was there before. So I don't know why HPN is necessarily more powerful, but from clinical reports, it appears that it is. And so it seems an advantage that we're able to stimulate the brain in a very powerful way with not a lot of current flow, which makes the whole technology safer in my mind.